Okay, good morning. Okay, let's finish that example we presented at the end of the previous lecture. And then we'll get on to new topics, okay? So this is a relatively more complicated example to construct a model giving certain system. And for this particular system, there are two masses attached to spring and damper and another spring at here. As we discussed at the end of the previous lecture, the difference between this system and the previous example is this is a 2 degree of freedom a 2 degree freedom mass spring damper system. And the reason it has 2 degrees freedom because you have a movement of M1, you also have movement of M2, so there are two movements at here. And as you can see later, the motion of M1 and M2 are actually coupled, so they affect each other essentially. Okay. So how do we establish a model? By establishing a model, basically means construct a mathematical equation or set of equations in this case to describe this system. The procedure is always as simple ones, just like simple ones. First, identify the objects, okay, or where the degree of freedom is. In this case, you have M1, M2 at here. Isolate, okay, each one of the objects. Okay, so isolate each one of the objects and draw free body diagram. So draw FBD for each object. Okay, so we have two objects at here. I'm going to move this down a little bit. Okay, so draw free body diagram. Basically, you look at M1 in here and sketch all of the external forces onto this object M1. So let's draw the easy one. So you have F of T at here, which goes down. Okay, so that's the first force. And then you start to look at the component, the mechanical component connected to the M1. There are two components connected to it. One is the spring, the other is the damper. And the nature of spring and the damper will always provide what? Restoring force in opposite direction of x1. Right? So the nature of this damper or spring will provide restoring force to anything connected, to anything connected to it, but to the opposite direction of that end. So this is x1 right now is going down, right? So there should be a restoring force from K1 goes up. There should also be a restoring force from B1 goes up. But how much is that restoring force then, right? So that's where you will have to use that formula for the spring and damper. But in this case, the spring and damper, both of them have what? Have two free ends. Okay, both of them have free ends at both sides here. Spring has K1, X1, spring has X2, and so is the damper. So the restoring force, so you could you can write it down separately. Restoring force from K1, okay, from this spring K1 is K1 times x1 minus x2. So x1 minus x2, okay, is the net change for the spring length. This is a restoring force, and this restoring force will be in the opposite direction of x1. So basically, you will have this restoring force pointing up. Okay, so pointing up. Now you might wonder, why do you use x1 minus x2? Because we're looking at it's this end at here. Okay, so that's why you use x1 minus x2. So when we do the M2, you'll see it will actually use x2 minus x1. Okay, yeah. So this is the restoring force from spring K1, and then restoring force from the damper B1. Restoring force from B1. Now, for this one here, I'm talking about, this is for mass number 1. Okay, it's for mass number 1. So for B1, you have B1 x1 dot x2 dot, and that also goes in opposite direction of x1. So you write down this B1 and here x1 dot x2 dot. Right. So the the damper restoring force is proportional to the velocity. Okay. So the faster it goes, the stronger restoring force or resistance force you will feel. Right. And that's all about M1. So M1, there's 3 external forces. Okay, and that's it. Any question on the M1? Okay. M2. Before we draw the M2, let's think about it. How many external forces acts on M2 in this system? How many would act on M2? 4? 3? Yeah. So there should be 3, right? One comes from K1, one comes from B1, and one comes from K2. I see some students say 4. You might think this F is the number 4, but the F does not directly apply to M2. It applies directly to M1, right? So you cannot count F of T as external force on M2. Okay. So there are 3 of them acting on M2. So for M2, number 1, there's going to be a restoring force from K1, and this time, because you're talking about this end at here with respect to K1, so the restoring force will be K1 x2 minus x1, and this force again is in the opposite direction of the degree of freedom, which is x2. So you draw this as K1 x2 minus x1. Okay. Yeah. And similarly, you have a restoring force from B1. So that'll be B1 times x2 dot minus x1 dot. So that also goes to the opposite direction of x2. So B1 x2 dot minus x1 dot. Okay. Now we've got these 2 done. Then let's look at the K2. K2 will also provide a restoring force. Okay. And for K2, it's one end is free and the other end is fixed. So the K2 will be simply K2 times x2. Okay. And this K2 x2 is also to the opposite direction of x2. So you should draw this force in opposite direction. You can write it at the bottom here, that's fine. K2 x2. Okay. So all of the three restoring forces are in the opposite direction of x2. Okay. And the magnitude of each one of the forces are calculated like this. So at this here, you just have to be careful is, there's a restoring force to the opposite direction of the motion. So how much is that, right? Really even for the same component at the different ends, you have this sign difference here, right? Yeah, one is here is x1 minus 2, this one is x2 minus x1. Okay? And that's the whole free body diagram for both M1 and M2. Okay. And once you're done with this, then you would apply this Newton's second law. Okay. So apply Newton's second law to both of these equations, both of the objects. Let's look at M1 first. Yes?
For the M2, is that also equilibrium? All the force going up and no force going down?
Okay, equilibrium, yes. All of the force, okay, so this is where I always emphasize. We draw the force going up, right? But it doesn't necessarily is the actual force that actually going up. Because what you draw here is the reference value. It includes the cases maybe going up, maybe going down. Look at this force, K1 times x2 minus x1. If x2 is greater than x1, that force is actually going up, right? But if x2 is less than x1, this force is actually going down. Okay? Yeah. But doesn't matter whether it's going up or going down. Your reference, right? You draw your reference x2 is going down. So the restoring force needs to go up in reference to the direction of x2. You see the difference, right? This is where oftentimes we struggle because we try to deal with the actual numbers. But what you need is a general description. So this is a general description here. You can always plug in some numbers, x1, x2, into it, and you will see, okay, so that for that set of number, it's actually this way. For that set of number, it's actually the other way. Okay. Okay. So let's look at the Newton's second law for M1. So for M1, Newton's second law says M1 times x1 double dot. Right? M1 times x1 double dot is m times acceleration equal a total number of the sum of all the external forces. Right? The sum of all external forces. So here are all of the external forces. And then you put them together, you sum them together. When you sum them together, you have to keep in mind what direction is the positive direction. Okay, and then you use whether it's a positive or negative value. In this case, your x1, x2, this is your positive direction. Downwards is positive. So f of t, you keep it as a positive. But these two right here, they are negative, right? Okay. And we can simplify this. We move all the x1 term to one side. We get m1 x1 double dot plus b1 x1 dot minus x2 dot plus k1 x1 minus x2 and equal f of t. Okay. This is your equation for m1. And for m2, m2x2 double dot. m2x2 double dot. m2 has three external forces. All of them goes up. So we need a negative sign for all of them. So we get negative k1 x2 minus x1, negative b1 x2 dot minus x1 dot minus k2 x2. And then we move all the x terms to one side. So we get m2x double dot plus b1 x2 dot minus x1 dot plus k1 x2 minus x1 k2 x2 equal to 0. Okay, so you have an equation here and equation over here. That's right, I should draw this one, equation here. Okay. And that's the end of this question. So in terms of the model construction, you constructed two equations or set of equations describing the motion of the system. As you can see, this is both of them. These are what we call the second order differential equation, which I'll talk about shortly. Okay. And each one of the equation has both x1 and x2 or x1 dot x2 dot in it. Okay. So this is what we call it's a coupled equations. Okay. Coupled equations. So what does a couple means? Essentially, if you have a motion in x1, it will affect the motion in x2 and vice versa. Right? If you are able to, later, well, maybe not in this course, you actually can solve this, and you will be able to see the difference or the connections between these two degrees of freedoms. Okay. So my expectation in terms of the model construction for this course, okay, because we're talking about, yes?
Shouldn't the spring force and damping force on that second mass be positive, not negative?
The K2?
Yeah.
The K2 times x2, it's still a restoring force, which is to the opposite direction of x2. That's why I draw the arrow here pointing up, right? So when you construct using Newton's second law, because that's to the opposite direction of x2, so that's why we still have a negative at here. Does that answer your question? Yeah? Okay. You will come to me after class, okay? Yeah. Any questions? All right, so again, my expectation for future is for simple system, like the kind of mass damper system or simple circuits, right? You should be able to come up with this second, because maximum we're dealing with is going to be a second order differential equation, and this is actually an extreme. Most probably we're not going to deal with a multi-degree freedom system. Most probably will be just a single degree of freedom. Okay? Yeah. So. Alright, so let's look at now getting into the new domain, which is the differential equation. Okay. First, we're going to look at is some of the concepts on differential equation. Okay, some concepts. Instead of directly diving into differential equation, let's look at the concepts first. I believe we have already seen differential equation, okay, and we just didn't formally introduce that. Okay. So I'll use dE to represent differential equation. There are a number of things. Number one, you have the concept of a dE. Okay, so let's look at the differential equation first, and then we'll slowly transition into ordinary differential equation and partial differential equation. Okay? Yeah. Okay, so what's the definition of DE. DE is probably the most the top level of the definition. Okay, as you will see, it basically covers the subcategory of the differential equation that we're going to introduce. Differential equation. So DE is an equation which involves an unknown function. So whatever the function is, okay, and its derivative. So that's a DE. Okay. It's an equation involve a function and its derivative. For example, right? Let's say, for example, if you have a RLC circuit, right? So you can have a DE like this. Okay, so this is a DE. So if you look at this differential equation, it has a function Vc, which is maybe a function of time. This is unknown, so we don't know what it is. Okay, this is actually the output, we basically call it. And this equation involves derivatives of this Vc. There's second derivative, first derivative, and no derivative here, right? And you can also have a case like that. So this is another example, partial okay. Here's another example, which we have just seen in 248, right? What do we call this equation again? That's right. There's a special name for this equation. It's called Laplace equation, right? Yeah. So this equation involves an unknown function, two variables, u, and involves its partial derivative of that function. Okay. So this is another example of a differential equation. Okay. So you see the difference. This one here is just a straight D, but this one is a curl D here, right? Yeah. Now this one we call that this is order number 2. This is also order number 2. Okay, so second order differential equation, and I'll tell you what exactly do we call them order. So order basically is the highest number of derivative represents the order of the system. Okay, that's differential equation. As you can see, differential equation includes both this partial derivative and this straight derivative, which we basically call it ordinary next. Okay. Yeah. Okay. So the next one is slowly into more detailed branches. So next one is called ordinary differential equation. Okay. So what's ordinary differential equation? An ODE is a special kind of a DE. So ODE is a differential equation. But in this case, this differential equation contains function of only one variable, okay, or one independent variable. so single variable function, and one or more its derivative. So if this function is single variable, basically its derivative just become just single variable function derivative, right? Okay, that's ODE. So I'll give you an example right here. In general, for example, let's say if y is a function of x. Okay, if you have a function y and the x is the variable. All right, yeah. So an ODE can be written in the following two different formats. The first format is this. So this is the first kind of format, which is not the kind of format we typically deal with. Okay, so essentially you have the derivative, multi-derivative of this function y. Okay, in general, it goes up to the order n, and then you have the original variable x at here. Okay, so this one here, if your ODE is written in this format, we call this is implicit ODE. So implicit, very much like the explicit, implicit function. So if you recall in the other course, when you have an explicit function, basically says z equal to f of x, y, right? If you have an implicit, then all of them are mixed together in one side. You don't have a specific expression for the z. That's called implicit, just like this one here. Okay. And the other format you can also write it into is could be y prime, y double prime, and up to y to the order n minus 1, and then equal to the highest order derivative of the y. Okay. If you can write this ODE in this format, so this is called explicit ODE. Explicit ODE. And this is the case we will typically deal with. Okay. So I'll give you a couple examples that are here. So for example, if you have mx double dot or m dx squared over dt squared equal to the external force F, this is essentially Newton's second law, right? You know, you apply a force to a mass, point mass m, and with the displacement x, so you get this second order differential equation. So this is the ODE, and this is also an explicit ODE. Okay, yeah. Okay, so let's take a look at another example. A very interesting example. People have studied so many years, and people use this for illustration in many different applications. Is a pendulum example, and you can also extend to double pendulum. Right? Pendulum example can be also considered a single link robotic system, basically. Okay? So if you have a pendulum system here, for example, you have a mass attached to one end of the string, and consider the string is massless and everything is concentrated at the point mass m. And if you lift it up, okay, with an initial angle of a theta, the length of the string is L. Okay? So we would be interested in what would be the equation of motion for this system, for the pendulum. Okay. Yeah. So I'll give you a simple example here, and then I'll show you how you can model. This is essentially another example of model construction. Right? How do we construct this model? To construct the model, you follow exactly the same approach. Take this M out, okay, and then draw a free body diagram, okay, for this M at here. Okay. And then we'll apply the Newton's second law. Okay? Yeah. Okay, so if I draw the free body diagram, you have a gravity force at here. Okay? Now you do have maybe a tension force along this string at here. When the pendulum starts to move, the pendulum basically will move, okay, with a linear motion, actually rotational motion, but at each instantaneous moment, you have a linear direction indicated by the x. Okay? And this x is perpendicular to the string. Okay? Consider the string is elongated rigidly, okay, with the stiffness. Okay? So this is x here, this is mg, and that's it. Okay? Yeah. So now, if we're talking about motion, we'll apply the Newton's second law, right, to the system at here. And Newton's second law is x mx double dot equal to what? Okay? Yeah. So mx double dot. Now we're talking about the motion along the x direction here, right? So as you can see, the t is perpendicular to the x, so it actually doesn't contribute anything, right, to the x. The only force contribute to the x direction is part of the force from the gravity force, mg. Okay? Yeah. So, and mg, okay, that equal to, what does that equal to? So that equal to, this is a theta here. So that's, which one is theta? This is theta here, right? This is theta. Okay? Yeah. So that's theta here. So mg sine theta. Okay, mg sine theta. A second here. We need a negative sign in here. Why do I need a negative sign? Yeah, my mind is not working. Why do we need a negative sign? Come again? To the opposite direction of acceleration. I think that's why, right? You do need a negative sign for now. Let me think about it carefully, because my mind is frozen to give you a better explanation. But my feeling is the force will be in the opposite direction of the acceleration. Because when it goes up here, so it accelerates, but then when it goes to this way, it will deaccelerate, right? Yeah. So you do need a negative sign here. Okay. And x at here, there's x and theta at both sides, and we wanted to make it the same symbol. So what is x? X is the, if I draw a circle here, okay? Then if this is the center of the circle, and this is the point mass at here, and this is x, and this is your theta at here, okay? Yeah. So your temporary x, okay, is basically equal to L theta. So the radius times the amount of an angle give you the arc length, right? Yeah, the temporary number. So x equal to L theta. So that gives you m L theta double dot equal to mg sine theta. Okay? Yeah. So move everything together, you can actually cancel the m on both sides. So you get L theta double dot plus g sine theta equal to 0. Okay. That's it. That is the basically equation of motion for the pendulum at here. Okay. Yeah. And this is a second order ODE, and it's explicit. Right. It can be written as this example here. Okay. So all of the examples that you see at here basically are examples that involve only one variable, only one function, whose the number independent variable for the function, there's only one. Okay? Yeah. And it could be higher order of derivatives. Okay. And this one here, as we're going to later on, this is actually a non-linear one. Okay? And this one here is a linear one. Okay. All right, so that's ODE. Okay, the next definition is PDE, okay, partial derivative equation. Partial differential. So we have seen this already. Okay, partial differential, a PDE, basically it's a DE which contain unknown function of multiple variable. Multiple variables and their partial derivative. Okay, that's partial derivative equation, partial differential equation. So I think we have seen quite a bit of already, but in general the writing can be something like this. So let's say, for example, right? Consider if you have a function u, and that is a function of n number of variables, okay, x1 to xn, then you could construct a PDE, okay, out of this u with any orders you want, okay, something like this. So it could be u, could involve u, could also involve just partial u over partial x, or partial u over partial xn, or it could involve higher order. Right, keeps going. Okay. So it can involve any combination of partial derivatives or any orders of the partial derivative. Okay, that gives you this partial differential equation. Okay. So some examples like this. Let's see, given a function u of tx, okay, u of tx. This is a very typical function you will see in heat transfer. Let's say you have a plate and you're interested in the temperature at a certain place and over time. Right? So this can be a temperature for a plate, so thin plate. Okay. And you can construct essentially a heat equation that is u of t equal to alpha times u of xx, like this. This is a heat equation, and it's a partial differential equation, and this is second order one, and alpha here is a positive constant, describes the rate of diffusion. Okay. So you can solve this. Okay. In upper level heat transfer course, you will be able to solve this, and you will be able to get the solution, and then from the solution you can study the transition of the temperature across this thin plate. Right. Okay. So that's a partial differential equation, and there are many other different examples you'll see. Okay. Okay, so now you have DE, ODE, and then PDE. Okay, so this different level of DE now, and one more level. Okay, special case is called linear ODE. Okay, linear ODE. This is more like what we're going to deal with, linear ODE. Okay. So I'm going to write down the linear ODE. Okay, what does it look like? Any linear ODE will take the following form. It's the form that we're giving here is a general format at here. Okay? It takes a form like this. And this is the general format for linear ODE with the order n at here, because the number here, right, is order n. Okay, and then I'll explain this a little bit here. Okay. First of all, it's ODE. As you can see, it is ODE because it involves a single unknown function y and its multi-order derivative, right? And the f at here, this is not unknown. This is going to be a known function. Okay? This is something what we call it's the input to the system. Okay? So the y at here is what we call, okay, later when we relate the system, is called the output of the system. Okay? And that's the whole point. Later we'll try to solve this ODE, right? To get the y of t, the solution for y of t. Okay, now the important part is I want you to know, if I ask you a question whether any given differential equation is a linear ODE or not, then the principle that you rely on is you basically look at the given one, whether the given one does actually stick to this format or not. If it is the same format like this, then you have a linear ODE. Otherwise, you don't have a linear ODE. Okay? Yeah. This alpha 0, alpha 1, up to alpha n of t. Okay? So those one at here, we consider them as coefficients, okay, due to system parameter. Okay, due to system parameters. So we'll give you example. We'll see how's that going to be. Okay. Yeah. So I'll give you an example right here. For example, if I have dx over dt squared times m plus b times dx over dt plus k times x and equal to f of t. And this is an example that we have derived for a mass spring damper, right? Simple mass spring damper system. Mass spring and damper with external force. So this is very much like this kind of system. So if you derive the equation motion for this, and you get this, right? Yeah. And this one, let's take a look at, is that a linear ODE or not, right? So what do? We compare this one with this format. So you can see it has nothing else but the derivative of an unknown function, okay? And the coefficient for each term is in the format of this. So this is a linear ODE. So what is a linear ODE? Linear ODE basically means this is a linear system. If you use this to represent a system, it is a linear system. So what does a linear system mean? It must be a system satisfying what property? Additive and homogeneous. Okay? Yeah. So that's basically what linear ODE basically means. Okay. I actually do have an example, but I didn't do that when we talk about the linearity. If you have an ODE like this, we can prove that this system will satisfy the homogeneous or additive, or in combination, the superposition property. Okay? Yeah. So basically, you can prove that if you have an input, for example, if I have a system cx1 plus cx2, if I have an input, if I have this as input, okay? Sorry, not this. Input, which one is input? F is input, right? F is input. If I have this as input, I can show that, I can prove that the output will be what? Output will be this. Okay? So if F1 produce X1, F2 produce X2, then when your input is this, we can show that the output will be this. So that's why it's called a linear ODE, or linear system. Okay. So how about this one here? Let me show you another one. How about this one? Okay. How about this one? Do you think this is a linear ODE or not? Okay, so this is the given one. What do? We compare this with this general format, right? Now if you look at the general format, there is no term that has the power of a derivative. Okay, so there's no term will look like this in the general format. So this one here, this is not a linear ODE, then this is actually what we call a non-linear ODE. Okay. How about this one? Y double prime plus y times y prime equal to 2. What do you think? Do you think this is a linear ODE or non-linear ODE? So compare this with the general format. If you look at the coefficients for all the y terms, none of the coefficient is what? Is a function of y. So none of the coefficient will be a function of y. So you cannot have y here as a coefficient. So this is basically not a linear. It's again it's a non-linear ODE. Okay. So how about this one? How about this one here? Is this a linear or non-linear ODE? So the difference here, this is not a constant, right? This is a time 2t. But that's okay. But you look at this here, this can be a function of t. Okay? So this one is actually a linear. Okay? But what is the difference? Let me finish this part here. What is the difference between this one and, for example, this one? So if you compare these two at here, the difference is what? Here's non-constant, here is a constant, right? Now, if you look at the mass spring damper system, I gave it to you, MBK. So in theory, I write it as constant. But I give you an example, if you recall that for a car suspension system, the K actually could change, right, as time goes on. So the K at here could be a time function. So the difference between these two at here, I can see it again. So this one here is a time invariant system. And this one here is actually a time variant system. Okay. And that's a fundamental difference. So basically, the second one here is a LTI system. But this one here is just a linear system, the time variant. Because the 2t at here. Okay? Yeah. Okay, so we'll finish with an example maybe in the next lecture, and then we'll get on to first order differentiation.